Greetings, my name is Juan Pablo Gonzalez, and I'm going to present an implementation of a modular algorithm for computing the common zeros of a polynomial and a regular chain. This is a joint work with Matt Calder, Professor Moreno Maza, and Eric Postman. This is the agenda for today. First, an introduction, then preliminaries, then we're going to explain a non-modular method for computing our algorithm. Then our algorithm is going to be a modular method. Then we're going to present the experimentations and the conclusions. The introduction. Most algorithms for solving polynomial systems symbolically proceed incrementally, that is, solving one equation after another, against the solution of the previous solved equation, or by projection and lifting, that is, by successfully eliminating one variable after another, and then proceeding by back substitution as in linear systems solving. The algorithm Triangularize of the Maple RegularChains library belongs to the category of incremental solving. We are not going to explain this in detail, but we're going to illustrate this with an example. Consider the system F of polynomial equations, and we want to solve this equation. So if we want to solve this equation, we start with the first one, y plus w equals 0. Then we took the second equation and we use this equation to do more computations. So we can see here that our computation is split. That means we try to solve the system with y plus w and 5 times w to the 2 plus y, and we see that our computation is split. Then we take the first equation and add that equation in the computations that we are doing. And we see that here our computations split furthermore. And if we add the fourth equation, we see here that we have 6 systems of polynomial equations. Now we're going to do a real life example. Here we're going to illustrate the algorithm Triangularize and how it proceeds by repeating calls to a procedure called Intersect. This procedure computes the common series of a polynomial and a solution set in terms of regular chains. So consider the system of equations given by f that we have here. First, we take f1 and we compute the intersection between f1 and the empty regular chains. We get f1 back here. Now we take f2. We compute the intersection between f2 and the previous regular chains. We get a regular chain here. Now with f3, we see here that when we compute the intersection between f3 and the previous regular chains, we get back 2 regular chains, one in dimension 2 and one in dimension 1. If we continue with this process, in F4, when we compute the intersection between F4 and the previous regular chains, we get back 8 regular chains here, as you can see. The first regular chain is dimension 1 and the other ones are dimension 0. This is important because now we are going to compute the intersection between F1 and the first regular chains, the one-dimensional regular chains, and we see here that we get back 2 regular chains. But the time that this takes is 1.63 seconds. And here we compute the intersection between F5 and the other regular chains, the zero-dimensional regular chains. And we see that that process only took 1.14 seconds. The above example shows that most of the time is spent computing the common series of polynomial and a regular chain of dimension 1. That is a space curve. This motivates the work presented here, where we propose a new algorithm for computing such intersection. Our algorithm is based on curve fitting techniques. The preliminaries. Let K be a perfect field. and k of x be the ring of polynomials in the variables x1 until xn. A triangular set T is a regular chain if either T is empty, or we can see T as the union of a polynomial with the greatest main variable, say b, and the other polynomials, say tb minus, and tb minus must also be a regular chain, and additionally the main coefficient h of T sub b must be regular mod the saturated ideal of tb minus. The saturated ideal of a regular chain T is just the quotient between the saturated ideal of tb minus plus tb and h infinitive. As an example of this, we have here T. We can see that the main variable of the first equation is x, the main variable of the second equation is y, and the main variable of the third equation is a. This is a triangular set, and we can check that the initial of the first polynomial, that is 2 times y plus b times a, is regular mod the other two polynomials. And also that 2 is regular mod the third polynomial. So this here is an example of a regular chain. Now, a final definition, the quasi-component of a regular chain, W of T, is going to be the algebraic variety of T, that's the set of zeros of T, minus the algebraic variety of H sub T, where H sub T is the product of all the initials of the polynomials inside of T. And the Zariski closure of the quasi-component of T is, in this case, the algebraic variety of the saturated ideal of T. Now, the algorithms Intercept and Triangularize. The Intercept algorithm takes a polynomial P and a regular chain T and computes regular chains T sub 1 until T sub E such that the algebraic variety of P intersection the quasi-component of T is inside of the union of the quasi-components of T sub 1 until T sub E. And this is a subset of the algebraic variety of P intersection the Zariski closure of the quasi-component of capital T. The triangularized algorithm takes a finite set of polynomials and computes a set of regular chains T sub 1 until T sub E, encoding the solution of the algebraic variety of F. That is, this is equal to the union of the quasi-component of T until T sub E. This is achieved by successfully applying intercept to the polynomials in T on the previously obtained regular chains. Now we're going to explain the non-modular method and its genericity assumptions. The goal: let K be a field of characteristic 0 or a prime field of sufficiently large characteristic. Let F, T, and B be non-constant polynomials in the order variables x, y, and z, and assume that the set capital T composed by T and B is a regular chain with main variable of T, x, and main variable of B, y. Assume also that the main variable of F is x. Our goal is to compute the intersection of the algebraic variety of F intersection the quasi-component of T in the sense of the function called intersect, as we previously explained. Now our genericity assumptions. Let S of T, F, and X be the subresultant chains between T and F with respect to the variable X. If the main degree of T is greater or equal than the main degree of F. Let also S sub 0 and S sub 1 be the subresultant of index 1 and 0 of our subresultant chains. And set R as S sub 0 and L as S sub 1. Our first hypothesis to fulfill our genericity assumptions is that R must be non-constant and must have main variable Y. Now let S be the subresultant chains between R and B regarded with respect of the variable Y, if the main degree of R is greater or equal than the main degree of B. And set S as the subresultant of index 0 and G as the subresultant of index 1 between R and B with respect to the variable Y. We denote as S bar as the square free part of S. Our second hypothesis is that the polynomial set composed by S bar, G, and L is a regular change. And as a consequence of this, we have that the polynomials S bar, G, and L are non-constant with respect to the main variables Z, Y, and X. The initial of G is invertible mod S bar, and the initial of L is invertible mod the idea generated by S bar and G. And finally, the algebraic variety between S bar, R, and B is equal to algebraic variety of S bar and G. Our last genericity assumption is that the initial of the polynomial T must be invertible mod the ideal generated by S bar and G. As a consequence of this, we will have that the vanishing locus, the zero set of F, the algebraic variety of F, intersection the algebraic variety of S bar, G, and T is equal to the algebraic variety of S bar, G, and L. And if we put all our hypotheses together, we will have a theorem that says that the algebraic variety of F, T, and B is equal to the algebraic variety of S bar, G, and L. So our computed S bar and G and L will have a set of solutions equal to our input system F, T, and B. Therefore, under our hypothesis, we have that the intersection between F and the regular chains of T and B is equal to the algebraic variety of S bar, G, and L. Now, an example to illustrate what I just previously said. If we have the polynomial ring with variables x greater than y and y greater than z, and the polynomial f, t, and b, and we compute the subresultant chain between f, t, and x, and we set L as the subresultant of index 1 and R as the subresultant of index 0, we can see here that in this case, R is non-constant and have main variable y. Now we can compute the subresultant chains between R, B with respect to y, and set G as the subresultant of index 1 and S as the subresultant of index 0. And now we can check that the initial of G is going to be regular mod S. The initial of L is going to be regular mod S and G. And the initial of T is going to be regular mod S and G. Now we can finally see here that if we compute this regular chains generated by S, G, and L, we will have the same output as the triangularize with input F, T, and B. Now, the modular method. The key ideas of the method are computing the subresultants R, L, S, and G by evaluating an interpolation. We use the Besu bound of the zero-dimensional variety V of F, T, and B for this evaluation and interpolation process. We verify the genericity assumptions as we recover L, S, G from the evaluation and interpolation process, and return error if one of these assumptions is not met. And we only use basic well-optimized functions of Maple. In particular, we use the ModP1 library to make the computations of the subresultant in 1 and 2 variables. The implementation. We run this implementation while we haven't enough images as 2 times the Besu bound plus 1. So we select a point and we specialize FTP at Z equal B. If FTB does not specialize well, then we go to the next point. This means that the degree of FT and B is not equal to the degree of their specialized image. Then we normalize the RegularChains T to TB. We compute the subresultant of index 0 and the subresultant of index 1 of T sub B, F sub B with respect to the variable X. We check assumptions about R here. If they are not met, we go to the next point, or we send an error if it's necessary. We compute the subresultant of index 0 and 1 between R sub B, B sub B with respect to Y. After we collect all the images, we interpolate these images and get S, G, and L. We apply rational function reconstructions to the coefficients of S, G, and L. We get the numerator of S, G, and L. Then we compute the square free part of S, and then finally we check that S bar, G, and L is a regular change, and the initial of T is a regular mod S bar and G. The experimentations. This here is the same example that we considered at the beginning. In this particular example, we can see that the time of intercept is faster than the time of our modular method. These are the SG and L for this particular system. And we can check that this system of equations will have the same algebra zero set as the answer given by the Intercept algorithm. Now, this is a more promising example. We have T, B, and F polynomials in degree 9. And we compute the time of the Intercept algorithm. We have a number close to 300. And in our modular method, we get 30 seconds. Now here we have a table with the degree of polynomial, random polynomials T, B, and F, the time of the Intercept algorithm, and the time of the Intercept by specialization. This is our modular method. And we can see that the smaller of our degrees, when we have a smaller degrees, the Intercept algorithm is always faster. But the higher the degrees are, we see that we start to getting more and more examples in which the Intercept, the modular Intercept, those is faster than the Intercept of Maple. And we can check that here again with polynomials of degree 8 and 9. We have to see here good numbers, 45 against 16. The conclusions. The theoretical aspects. We have presented here a modular algorithm for solving a three-variate polynomial system of equations, f equal t equal b equals 0 under genericity assumptions. To be more precise, this is a modular method for the called intercept of f and the regular chains of t and b. The article to be submitted to the Maple conference proceeding will explain how to relax the genericity assumptions. A follow-up article will extend this modular method to solve square systems with an arbitrary number of variables. The practical aspects. The preliminary implementations and experimentation in Maple bring promising results for the modular method. To be more precise, for generic input system of sufficiently large Bezout bound, the modular method outperforms the non-modular implementation of the command intercept. There is a large room for improvement. Indeed, this modular method opens the door to using speculative algorithms for computing subresultants. Those are asymptotically fast algorithms that compute the subresultant of index 0 and 1 without computing these other subresultants, while being able to resume the computations for obtaining the subresultant of higher index if needed. Thank you very much for your attention. I hope you enjoyed the talk.